here we go. We're going to talk about sets inducing large additive doubling. It's a combination of a few contributions from different papers. I'll go to that. So we start with this setup. So we can do pretty much everything. We're going to look at in a rather general setting of torsion-free groups, or maybe even arbitrary abelian groups. But for simplicity, we're going to work with sets in ZD, where D is some unspecified large dimension. So basically, you can think of our sets being embedded into some very large ambient space. They're basically integer lattices. Surely we are going to work with some sets, and the additive doubling is the primary thing that we're interested in. And next, what we are after is induced doubling of a set. So the idea is that we want to find out that what is the minimal doubling of a set such that our set is contained in there. So our set U is sort of a witness, so that if we know that this set U is contained somewhere, this larger set actually has at least that, the doubling at least that large. And it turns out that it's mainly about the dimension play, because certainly if you have just an integer set, then you can always have a very large arithmetic progression, and this quantity is not very interesting then. But if you have large dimensions, then it turns out that depending on your set U, you have some non-trivial results in that way. And the first result in this direction is, of course, what is called the Freiman lemma. It is not very hard result. Back in the 60s, I think it was proved, or in the 70s. So this is a starting point. So the next step would be to find a larger family of sets which induce large doubling. As like a spoiler here, one of the main results is that a certain generalization of hypercubes, which we call quasi-cubes, induce very large doubling, basically as large as it can get. This is not that rigid as a hypercube, so we actually have a pretty large family of such sets. And then we will look at what can we say about Freiman's lemma and the weak polynomial Freiman-I.Ruzsa, and how we can apply induced doubling in such a setting. So it turns out that the larger the family of sets we can construct, which provably contain induced doubling, the better information we would get about the Freiman's lemma and the weak polynomial Freiman-I.Ruzsa. So this is an outline of the talk. All right, so off we go. So it's a rather famous Freiman's lemma, and it's much simpler than the celebrated Freiman theorem, which says much about the generalized arithmetic progressions and how the sets are actually structured. But the Freiman lemma just says that if your set is proper dimensional, meaning that it's it contains non-degenerate simplex of dimension m, then it has additive doubling at least m, give or take. So here is the precise formulation here, and if you divide by the size of the set, then you will see that in this case, in the case of a simplex, of an m-dimensional simplex, we already have an non-trivial induced doubling of size roughly m/2. If we sort of discard this small term, which is, of course, at least, at most, m/2, just because A is a superset of the simplex. So we already have non-trivial results, but it's not even clear what is the actually exact bound here. Well, probably one can figure it out with some tedious calculations, but it seems that it's kind of hard to generalize for a larger family of sets. So this is a starting point. At the same time, of course, there is a feeling here that if we have a simplex, which is m-dimensional, and it's a pretty small set, then for larger sets, we should have also some non-trivial induced doubling here. And it turns out that the key observation is that instead of looking at an induced doubling, it's much more convenient to look at a rather weird looking combination. And instead of looking at the sets, which are supersets or set U, would take arbitrary sets A and B and look at how the tripling behaves scaled by the geometric mean of the sets. Actually, it took quite a lot of time for us to play around and realize what is the exact combination of these sets, just because if you, for example, take the sum of the sets or some other combinations, you will sometimes end up with a quantity which is trivially small, or on the other side of the spectrum, this quantity just doesn't give you any meaningful way to work with that. So we cannot actually prove anything with it. So this turns out to be a rather sweet spot here. And the main, so of course you can apply I.Ruzsa. So you have a decent bound for the alpha, which is induced doubling, if you're okay with the square root. But the key feature is that this beta is tensorizes. So what it means that if you slice your set into smaller dimensional pieces, then you can bound this beta of your set in terms of the betas of your slices. This is a fairly simple theorem to prove, but this is something that is already absent in the context of alpha. So it is not clear if something similar holds for alpha, probably not. So, and even this observation allows one to prove that beta of a hypercube is as large as it can get. So, because certainly if you take, say, A and B as singleton sets, then beta would be at least as small as U. So here, this is the largest that one can get here. And well, how you would prove that a hypercube has this maximal beta? Well, just apply this inequality d times, and assuming that you know that your beta of a 2-point set is just 2, which you can, it's not completely trivial, but it's fairly easy to prove. Then you just use this tensorization property, and by induction, you would end up with 2 to the power d. And it turns out that this is already a non-trivial result. It reproves what is called discrete Brun-Minkowski inequality by Green and Tao. And it gives you a rather flexible way to prove, because as you can see here, you can prove this kind of results not only for hypercubes, but a slightly more generalized set of family of sets, because here you just need that all these betas of your slices have the same beta. So here is how this actually works, just to show you an example. So this is a two-dimensional example. Here is your set U, and we have just 2 dimensions here, and your set U is just a combination of different slices. And if you know your beta for each slice, then you can bound the beta of your whole set U. Okay, let me just like stop for a moment, and maybe if there are any questions I can ask, people can ask, or how do you do that usually?
So people, yeah, feel free to unmute themselves if they've got a question, or there's a hand raising feature, I think.
Oh, okay, good to know. Then if yeah, people are confused, then I welcome everyone to ask questions just to not get lost in the middle. All right. All right, so this already gives us something, but the main problem with the theorem is that it's pretty much ineffective in the case when we have some slice, like in here, which, for example, has a small or tiny beta. In this case, it very quickly gives us a rather trivial result, right? Because we need that this minimum should be large in order to get some decent results. And in this, in order to cure this, we need to find out a way to somehow weight different slices, different fibers, so that, for example, if we have just a few small fibers, then we can still get a decent bound, just because we can weight them up in a reasonable way, and the large ones would dominate, the ones with the large beta. Okay, let's have a look at how actually our tripling looks like. So just by taking the first coordinate and assuming that our A is indexed by the first coordinate I, and beta B is indexed by the first coordinate J, we can simply write down how the tripling in multiple dimensions looks like. Because we just take the coordinate slices here, and hope this notation is not confusing here. And if we want to bound the size of this tripling, we can just use union bound and take the largest combination for each z. In practice, we have a union of different triple sums, but in our case, we are just taking the maximum of taking the largest for each slice. And then here we can apply by induction our beta for each slice. So here we have this universal inequality, which is surprisingly simple. And we need somehow to bound this sum in terms of A and B, in terms of the sums of I's and G's, in order to get something which is, in order to close the induction. Let us now reduce the case to use where we have only 2 slices. So meaning that we have only 2 indexes k where beta is non-zero. This is exactly what we call the quasi-cube. And then it's just a very natural generalization of a hypercube, where you just have 0 ones in each coordinate. So it's constructed recursively, and you start with a 2-point set with a 1-dimensional quasi-cube and a d-dimensional quasi-cube is a set such that when you slice it across a coordinate, or in fact among any 1-dimensional subspace, it has only 2 cosets, hx and hy. For simplicity, you can just think of coordinate slices here. So this means that every time you take one coordinate, and you can freely choose any coordinate you want, if it splits only in 2 pieces based on this coordinate, and each of these pieces is a smaller dimensional quasi-cube, you're on the right side. This is how it looks like. There's an illustration. So you take a d-dimensional piece, and it splits only into fibers here. And U0, U1 are d-1 dimensional, and each of them are in turn also split into just 2 pieces. And the key point here is that this x's and y's are not necessarily the same. So if we have here, say, 0 and 1 as the coordinates where we have the split. So here it could be, say, 3 or 5 here for U1, or like 2 and 3 for U0. So this is the main and only difference from the traditional hypercubes here, where you would always split only on 0 and 1s. Otherwise, it's pretty much the same. But obviously, it's a larger family of sets and less rigid. All right. So we are back again, and assuming that we split on 0, 1, which is not such a big loss of generality here, we rewrite our estimate in this way because we have only 2 pieces. And the key theorem here is that this sum can be bound in terms of betas of these 2 pieces only. And this allows one to close the induction in terms of a quasi-cube, just because this part, square root AB, is exactly what one needs in order to obtain a bound for the beta, right? Because once you divide by this quantity here, you would get exactly beta of u. And you could get that beta of u is greater or less than beta of u0 plus beta u1. And you would get that beta of u is exactly u. So it's large as it is get in case of a quasi-cube. Okay, so here I write discrete weighted PreCoppa Leydner inequality. So what's that? So first of all, let us recall the classical analytic PreCoppa's inequality. One would need to introduce max convolution for 2 functions. It's like a normal convolution, but instead of summing or integrating, you take the supremum over y here. And the classical theorem of PreCoppa is that the L1 norm can be bounded in terms of F2 norms here. In our case, let us see what happens if, for example, these betas, beta of u0 and beta of u1 are equal. And so instead of having an integral here, we have actually a sum. So sort of a discrete version of this PreCoppa's inequality would look something like this. This seems, it's not like completely that way, but it seems natural to guess that something like this should work. And finally, the needed version for this is to replace this 1/2 here with arbitrary weights of lambda. And this is a result which appeared in a short note with Ben Green. So it's 5 authors here: Ben Green, David Matlosci, I.Ruzsa, George Shakan, and myself. So the original paper contained a proof of this inequality through a combinatorial argument. But it later turned out that like a shorter analytic proof coming from this connection is possible. And as long as you believe in the theorem, which definitely looks like a generalization of this, and this in turn definitely looks like a discretization of this, right? So if you take these two leaps of faith, you actually can get this for free. Well, just because take lambda to be this weight, f to be ai square root of ai, g square root of bj, and then this sum. Okay, so let's start on the right-hand side. So right-hand side going to be just sum of AIs, and sum of AIs is just the size of the set A, because this is the size of disjoint fibers. And the same for B. This is the sum of the sizes of the disjoint fibers. And at the right-hand side, you have a square root of A and B. This is what we want. And on the left-hand side, we also have the denominator here, just because if again we can back together, if we divide by this bracket, we will have lambda and 1 minus lambda in H max. So, and just that way, we obtain that for quasi-cubes, we have the maximal beta that one can expect. This again follows very easily just because you apply induction and reducing the dimension 1 by 1, you always have that the beta is as large as the sum of the betas of the two fibers that we're splitting in. And since at the very end we have a trivial betas, which are ones, you end up that you have the maximal value here. And applying the I.Ruzsa here, we end up with a very strong induced doubling inequality. And this, so why this is strong? Just because this is one of the few cases where we do not depend on the ambient dimension. Because in the applications, typically you cannot you cannot calculate very efficiently the dimension of your set, because sometimes you use the Freiman's embedding, sometimes you use some information about the doubling, and the dimension parameter is usually very large. While if you apply it for, say, subspace theorem, you would need this to be logarithmic in size. Okay, so how exactly this works out? Let us see an example of what is called weak polynomial Freiman-Ruzsa. So there is the polynomial Freiman-Ruzsa conjecture, which predicts very precise information about the sets with moderately small doubling. But a weak version of it says that if you have a set in ZD with doubling k, then you can find an affine subspace of very small dimension such that it intersects A over a polynomially large piece. This is definitely a weaker version compared to the classical polynomial Freiman just because we have no idea how exactly this subspace intersects. And it may be very sparse inside, but it turns out that as Dmitrii Chang showed like more than 10 years ago, even this Vic version of the polynomial Freiman-Rényi conjecture is extremely helpful in the applications, mainly because you can apply subspace theorem, which requires only the rank condition. And this dimension, log k, is exactly the threshold where the subspace theorem becomes ineffective. So as long as you have something like a power of k or sublogarithmic here, the subspace theorem becomes trivial. And this logarithmic bound is sort of a main obstacle for the, I think that the state of the art for the polynomial Freiman-Rényi conjecture is some exponential exponent to the power of some power of log, something like this. Okay, so what can we say in this situation if we know that for some family of sets, alpha is large? Well, it's just a contrapositive statement that says, okay, if we have a set A with doubling k, it's just simply that A cannot contain subsets with induced doubling k, like as simple as that, right? Because it's just a contrapositive statement. So in our case, this means that A cannot, if A has a doubling k, then it cannot contain quasi-cubes of size square root k, say. And it turns out that you can extract a certain structural information about sets which are free of such families. It is arguably a much weaker statement than the conjectured weak polynomial Freiman-Rényi, but still it allows one to deduce something meaningful in the regime where k is as large as some power of a. And to my knowledge, we don't really have any tools whatsoever to argue about the structure of additive sets with rather large additive doubling. So we have very good tools like harmonic analysis and Fourier in the regime where k is just below the logarithm, but when we are above that, basically the Freiman lemma was the only thing that we can use, and it is typically very wasteful. Just so okay, what exactly this coordinate query complexity means? Assume that you know all the elements in your set, and you know that they are contained in a very large dimensional ambient space. And you're allowed to ask an oracle a query pointing out at some coordinate and asking what is the coordinate value. So once again, the setup is as follows. So you know that there is some set, and the oracle says things, takes some element in secret, and your goal is to find out what is this element. You're allowed to ask a coordinate query. Basically, you point out some coordinates, say like fifth coordinate, and ask the oracle what is the value of this, what is the coordinate projection to this. And you want to make as few queries as possible in order to find out what was the original element from the set. So here's an example. So in this case, you just follow some algorithm in order to do that. So for example, here you take the third coordinate, and the oracle says, okay, the third coordinate is 2. And then, all right, so the third coordinate is 2. Then I query the 6th. Here it says, okay, this one is 5. And then, okay, in this case, I'll open the last one. There is 7. And then you say, okay, 2, 5, 7. And at this point, you're supposed to find out that, okay, there are only one element in the original set with this 3 projections. So I can give an answer straight away. So this element is like this. In a different case, assume that the answer for the first question was 4. And in this case, you actually have, you say, okay, in this case, it is 4. Then I ask the 5th coordinate. And after that, I ask for the 6th. So the main point here is that the queries that you're asking depend on the answers from the previous steps. And the coordinate query complexity is the maximal amount of queries that you need in order to get an answer in any case. So let us see how it actually compares to the weak polynomial Freiman-Ruzsa. Assume that it is true. In this case, this game would have been rather trivial just because you just take this intersection as your a prime here, and you know that this intersection is contained in an affine subspace of Frank log k, which means by high school linear algebra that there are log k coordinates, so that if you take the projection there, it's injective. So you just fix this coordinates and ask the queries about the values in this coordinates one by one. And since it's injective, you just get the right answer once you know all these coordinates. And here we have a much wider set of opportunity to ask questions. So this turns out to be quite effective in the case where we use, how to speak. So this turned out to be exactly very effective in the situation where you need to prove some product application, namely the theorem called few products, many sums. I do not want to go into that details, rather want to concentrate on the possible applications in here. So when this theorem is not effective, exactly in the case where you have sort of a randomly looking set, just because if you take some random points, typically even the projection in a single coordinate is injective. And this is like a very big limitation here. this limitation comes from the fact that we know that kind of bounds only for the families of sets where we have only two coordinates to begin with, like quasi-cubes. So we know that our set is free from quasi-cube pieces. And if we somehow can extend the family of sets for which we know that the alpha and thus beta, or other way around, is large, then we can actually gain a lot more insights of how sets with small doubling can look like, or rather what they cannot look like. And this reduces the possibilities here. And this motivates the following conjecture, which I believe is the central in this whole study, which started as a framework for studying like induced doubling and finding the right tools for doing this. And the conjecture that we call linear metroid conjecture says that, in fact, this quantity beta is very coarse invariant of the set. So in fact, if you take all the subsets of your set and look at the dimensions, this is actually what really matters. And for example, if you have a just single dimensional set Z, then no matter how you try, your alpha is going to be 2 and the beta as well, just because you can place this in a very large one-dimensional progression. And the only play that we have for higher dimensional sets, it's the dimension of the pieces. And assuming that we have this characterization of betas in terms of the dimension we have, we can construct a much larger family of sets for which we know that beta is large, because we can take our quasi-cubes, for example, and blow up and disturb them in a pretty much arbitrary manner. And this, I believe, what gives us a better feeling and handles of the sets with small doubling. All right, so I think this is the culmination of the whole talk, and I would stop here without doing any digressions. And I would be happy to answer any questions if there are any.
Great, thank you. Well, first, if we give Dmitrii a round of applause.
Thank you very much.
So if you do have any questions, either unmute yourself and ask them, or use the raise your hand feature. Please do fire away, or ask them in the chat if your microphone's not working. So perhaps I could start with a not a very low level question. Can you just go over again what this linear matroid conjecture would give you with respect to previous results, how it would improve previous results?
I don't have any like exact statement, but it would definitely help more or less straight away in the applications for in the combination with the subspace theorem, just because in this case, in the subspace theorem, you would typically have a situation when any subset, if you take, for example, a set of solutions to an S-unit equation in lying on a multiplicative group of arbitrary rank, that you know that any subset, that if you restrict this subset to any dimension, to any subspace of dimension k, the intersection is at most exponential in k. This would mean that this actually looks like a quasi-cube, just because this is exactly how a quasi-cube look like. So you cannot have too many elements in a subspace of small dimension. And in turn, that would give you the information about the beta of this solution set, which would mean that your solutions cannot be contained in a set with small additive doubling. And this is how you would, for example, theoretically resolve the few products many sums conjecture, which is a special case of the R-similarity sum product.
Mm-hmm. Mm-hmm.